Chromebooks are like pretty inexpensive. But insurance is like $25 a year. They gotta make like a pretty good amount of money. There definitely isn't that much.
Can I drop some knowledge on you?
Go for it.
Insurance companies make lots of money.
Yeah. But like,
there's two things I get in the mail every day almost. I get a credit card offer, and I get some sort of life insurance policy offer. Almost every single day.
I love life insurance. If I'm dead, I'm already dead.
But then people who, your relatives get money.
I mean, true.
But anyway, so like, why do credit card companies and life insurance companies send me offers? Two reasons.
they love money.
They love money, and the other reason is they've recognized, Alex Barazan has a good credit score and is not an idiot with his money. Therefore, this is a safe investment, and we just make bank off of it. All right, I'm going to teach chemistry now. So welcome. We're going to continue redox. The second hour yesterday, we were a little slower, but that was okay. There was just more questions, and that was good. So if you were at home and watched the video, or if you were in the first or third hour yesterday, we got right here, okay? For those of you in the second hour, you didn't really miss much. I was going to write that word in, all right? So let me recap from this point on. I'll give you 2 minutes of yesterday's class, then we'll keep trying some more oxidation numbers. Oxidation and reduction are opposites. If I have a half reaction, which is called oxidation, I can reverse that whole thing, and it's reduction, okay? Remember, oil rig, when you talk about oxidation, you're talking about a substance losing electrons. When you're talking about something being reduced or reduction, that is a substance gaining electrons. Okay, so we are going to hopefully get to the balancing stuff today. Not hopefully, we will get to the balancing stuff today. But let's plow forward with some oxidation numbers. Okay, the vast majority of these are pretty straightforward. The two tricky ones are number 3 and number 4 because they don't have oxygen or hydrogen. The rules for doing this are on the previous page. Okay, the big takeaways are hydrogen is almost always going to be 1+. Oxygen is almost always going to be 2-. And then the other pieces for oxidation number just kind of fall in place, right? Your total, the total charge on whatever you have, must equal the total of the polyatomic ion. I think all of these in here are polyatomic ions. I don't know if I even have any neutral compounds. I don't. They're all polyatomic ions, okay? So the charge might be different. Sometimes the total charge on that polyatomic ion is -1. Your oxidation numbers must add up to -1. Sometimes the charge is -2. Your oxidation numbers must add up to -2, right? Keep going. Slowly but surely, I'm going to start revealing some answers, but I want you to struggle with this. And if 3 and 4 are throwing you for a loop because they don't follow the rules that I've given you, skip them. That's fine. I'll come back to them and I'll explain why they are what they are. Okay? Talk to each other. That's a good idea. That's always a good idea. And I'll give you a head start, and then I'll start chipping away at it. Once you get going, this should be pretty, hopefully, easy-ish. Might have to knock off the rust a little bit from last year, but I think once you get going, it should be fun. Would you like me to keep the rules on the smartboard? Would that be easier?
Oh, yeah.
I can do that. All right, I take it back. By the way, for those of you at home, we do have supply pickup again Thursday, Friday. So if you are a virtual student, you can pick up your stuff Thursday, Friday. If you're an B student, sorry, you guys are A, right? I'm sorry. If you're a B student, you'll be here next week and I can give you your packet. Don't worry about picking up AP Chem stuff. If you're an A student, I'll give it to you Thursday. Okay? Make sense? So unless you are missing days somehow, some way within that time period, you shouldn't need to come in unless you're a full virtual student on Thursday or Friday to grab that. Because A's, I'll give it to you this week, B's, I'll give it to you next week. But just to put that on your radar, as it's rattling around in my head. Jagger, what's up?
If this were like a normal school year, would we have ever used those textbooks?
Yeah, we will later too. Yeah, the hard part is just checking them out to a hybrid model. So I kind of played it safe because I don't want to lose them. Because they're nice. Well, I just don't trust seniors who are in a full virtual setting to bring my book back.
Why don't you just like scan a copy of the need and then that post that as PDF?
Because that's illegal.
Well, why don't you just tell me
Really?
it's like fair? Well,
Kind
no,
of.
if it's fair use, like if you put the whole book online, yeah, it's not.
So in theory, I have access to a digital version of that textbook, but I have tried it for the last couple of years and it keeps giving me problems. Like, I don't know. So we will need it eventually once we start getting the thermal, because we need some constants from that book and you're going to be constantly looking them up and it's nice to have that. So somehow, some way, you're going to get some form of an appendix from that thing in a second. Whether I give you a hard copy or whether I give you digital access, well, maybe both. Ideally both. All right, I'm going to start chipping away a little bit, okay, and see where we're at. Bisulfate. If you're looking for these, by the way, I didn't give you the formulas for half of them, and I didn't give you the names for the other half, right? I was just being a little annoying. I think all of them are on your last year's periodic table, with the exception of maybe one or two, but I think they actually are all on last year's periodic table. This is the HSO4, 1 minus. Hydrogen is 1 plus, because it's always 1 plus for oxidation number. Oxygen is 2 minus, because it always is. That leaves the sulfur. Again, it's just math, right? I have 4 oxygens at 2 minus each, for a total of 8 minus so far. I have a hydrogen with a 1 plus, which gets me to -7. The total needs to be -1, right? So what does the sulfur have to equal in order to get this total to -1? It's not rhetorical. What does the sulfur have to equal in order for the oxidation numbers to all add up to -1? 6 plus. Okay. If you didn't see that beforehand, let's go through it one more time, right? It's just a math thing. I know the hydrogen's 1 plus. I know the oxygens are all 2 minus. I have 4 oxygens. They're each 2 minus. That's -8. I have 1 hydrogen. That gets me to -7. In total, I need this to be 1 minus. The sulfur must be 6 plus. Right? The next one and the one after that are the weird ones like I was talking about. This is called thiocyanate. Okay? It has a 1 minus charge. Now, there's no oxygen, there's no hydrogen, so I didn't really give you a launching point. If you ever come across one of these, there's a good chance that the charges are just the common charges, or I should say that differently, I'm sorry. There's a good chance that the oxidation number matches the common charge. So if you go to the front of the periodic table and you find sulfur, it's in column number 6 or 16. What's the common charge of a sulfur? 2 minus. Most likely, the oxidation number matches the common charge. It's not perfect by any means, but it's a good place to start at the very least, okay? So sulfur is 2 minus. Carbon is, it says plus or minus 4, right? But what's nitrogen? 3 minus. So if that's 3 minus and this is 2 minus and I need the total to equal -1, what do you think carbon should be? 4 plus. Yeah, okay. So it's a weird one. I won't really do that to you moving forward. But it kind of was solvable, so to speak, if you just looked at common charges. The next one is ferrocyanide. the 4 minus charge? I forget. Is that it? Right? FeCN6. I haven't looked at that one in a while. I'm sorry, I don't use ferrocyanide very often. So, the cyanide. The cyanide part is its own polyatomic ion. What's the charge of a cyanide? It's 1 minus. So if we know that the cyanide is going to be 1 minus, the iron we can calculate separately. Again, this is a weird one. I know it's a weird one. Okay? But I'm going to do the iron first, actually. Because I know that these, I have 6 cyanides. Each cyanide is 1 minus. So the iron must be 2 plus. Catch my drift? Okay, it's weird. Again, I won't do this to you anymore moving forward. But I'm just using the total charge and the fact that I have 6 cyanides. Each cyanide, if you look it up independently or individually, is 1 minus. So I must have this iron be 2 plus in order to make that work out mathematically. Now, the carbon and the nitrogen within that cyanide, that's a different story. We could go a couple different ways with it, okay? And in reality, we'd probably want to be looking at the Lewis diagram to figure this out. But it's not worth our effort. It's not really tested, so forget it. The nitrogen is going to be its normal charge. The carbon is going to be a weird charge, and we'll leave it like that, okay? Those are the weird ones. There's no more weird ones after that. All the other ones can be mapped out or deduced out. So I apologize if that caused you anger. Move forward. The rest of them are all solvable. Keep going. I'll leave that up for a second just in case you missed anything, and then I'll try the rest of them with you. And again, please try these. Go through the struggle just a little bit. If you cannot get oxidation numbers, you're not going to balance the redox reaction. It's not going to happen, okay? So please try these things because you need to be able to do this before we can do the next part. And if you got a good chunk of them done, or if you got all of them done, check with the neighbor. I suppose that applies to the people here, not at home. Don't go to your neighbor's house, please. It's a pandemic, for crying out loud. Don't do that. Hey, can you check these? If I was your neighbor, that would work out well. I probably live close to some of you. Probably. I live in the Satine area. Probably. Huh? Not quite. It's I live off of Hilltop. So Hilltop's like the one that comes straight from the hospital.
Yeah. I mean, you.
I don't know. Where's you? I'm not that far. Is that further out? That's yeah, I'm not that far. I am on. I'm close to the hospital basically, but like on the Satine side of the hospital. Why? So you want to egg my home?
Yeah. That wasn't what I was. We're gonna come over for a class field trip. Yeah.
Oh God. Why? I wouldn't wish that. I wouldn't wish that upon my worst enemy. Those two are crazy.
How old are they?
6 and 4.
Boys?
My son is 6. My daughter is 4.
Oh.
Sorry, I should take that back. My son's pretty in control. My daughter's crazy. I always like to throw her under the bus. Because she's adorable, but she's just a little crazy. Really looking forward to the teenage years. No, that's sarcasm.
Okay.
Through
I
and
was
through.
gonna say, yeah.
She acts like a teenager now and she's cool.
You do that Rocket League?
She's awesome.
Really?
Yeah, she's a plat too.
Wait,
Okay, bromate.
what was that conversation?
I'm sorry, people at home. I can only imagine how much you love live class. Bromate. What's the formula for bromate? The what charge? Okay. Oxygen's always what? Okay, what's the bromine? Awesome. This is called what? Oxygen's always what? Hey, do you see that last column? Those are oxygens. Okay, sorry, just going on autopilot here. The chlorine. If the oxygen's 2 minus, I've got 4 of them. That gets me to 8 minus. I need the total to be 1 minus, so the chlorine must be. Okay, a little funky. Have you ever heard of a 7 plus chlorine? No, but remember, this isn't charge, right? It's related sometimes, but this is not the actual charge. This is called oxidation number or oxidation state. So it is unique. It is different in a subtle way, but that looks kind of funky. Chlorate. Oxygen's 2 minus, chlorine must be 5 plus. Chlorite. Oxygen's 2 minus, chlorine must be 3 plus. Hypochlorite. Oops, well, they don't need the 1. I was counting down. Oxygen's 2 minus, chlorine must be 1 plus. Nitrate. I'm going fast, but I hope you're done. Or at the very least, hanging with what I'm up to. Slow me down if you have a question. That goes for you at home too. If you, I think my computer's muted, so good luck trying to talk to me. There we go. Now you can talk if you'd like. I was gonna say I unmute and all of a sudden something bad happens. 3 oxygens here. That's 6 minus. The nitrogen must be 5 plus. That's an ugly 5. There you go. That's a moderately okay 5. Questions? Concerns? You want me to just keep plowing forward? All right, let's do that. Sulfite. Oxygen is. I'm assuming these all have oxygen. Feels safe. 2 times 3, or negative 2 times 3 is negative 6. The sulfur must be 4 plus. Sulfate. Oxygen is 2 minus. That's total 8 minus. The sulfur must be 6 plus. Nitrate. Oxygen is 2 minus. The nitrogen must be.
Yeah.
I was waiting for you to participate, but apparently I'm just on my own. Permanganate. What the heck's the formula of that? With the what? 1 minus? Okay. Oxygen is 2 minus. Or the manganese must be 7 plus. This thing's called chromate. Oxygen is 2 minus. The chromium must be 6 plus. Sorry, hold on. That was quick. You didn't get those. This is old news. That's kind of why I'm plowing forward. Because in theory, you did this last year. But this was also like post-quarantine, I heard. So that theory is getting less and less.
Yeah, the end of the year,
We're slowly approaching our 3rd semester of quarantine. How exciting.
You never had to turn in any homework, or like we did
That's
some
for fancy
paper
folk.
where like you really didn't have to do much. So like,
Yeah, I think the entire world was just kind of running around like on fire last spring. That was. Same with Colorado for a
They
while.
always are, though.
They kind of are. This is dichromate. I'm assuming. I assumed correctly. Oxygen's 2 minus. I've got 7 of them. That's 14 minus. That's a bunch. I have 2 chromiums. That's a little funkier math, isn't it? This is the one that I have as the example in the rules. If you go back to the rules, when it's talking about how the total needs to equal the charge, I use dichromate as my example because it's probably one of the more difficult ones. But I need a 12 plus from the 2 chromiums to equal the total of 2 minus, right? So each chromium individually must be 6 plus. Okay? Oxalate. That's C2O4. All right, good job, brain. Oxygen's 2 minus. Each carbon is? A little unique. Borate.
You got it.
No. Is it 3? All right. You guys have somebody new tomorrow. I'm sure they're a nice person. Okay. All right, borate. Oxygen's 2 minus. That's 6 minus total. The boron must be. That makes plus. That makes sense. I should have known that. Amateur. Phosphate. Oxygen is 2 minus. The phosphorus must be 5 plus. Extremely fast. I hope you at least tried some of them. Again, the rules are on that first page, and it's not too bad. It's hydrogen's 1 plus, oxygen's 2 minus, and then get the total of those oxidation numbers to equal the charge, right? So there is a smidge of math, there is a smidge of thinking every now and then with these. But like I said yesterday, and like I said to start class today, if you can't do oxidation numbers, you have no chance at the next part. So just forewarning, okay? Now, oxidation numbers aren't always this difficult either. Okay, I gave you a whole bunch of polyatomic ions on purpose because that requires you to do a little math. Sometimes they're really, really simple, like we'll see in our first example here. By the way, oil rigs over here. If you want to fill that in, you're welcome to. We talked about that twice yesterday, so I think we're okay. Okay, here's the directions. Refer to your rules on the previous pages if you run into complications. Put oxidation numbers above everything. Write and balance the oxidation and reduction half reactions. Multiply the half reactions to balance out the electrons so that you cannot lose or gain more electrons than the opposite. Okay, right? I can't lose 5 electrons and gain 3. Where'd those other 2 go? I can't lose 3 and gain 5. Where the heck do they come from? Right? It has to match. So we'll cross that bridge in a little bit. All right. We're going to go through the rules step by step to solve this. Okay, you've done this before. You might have done this exact example before. But I would strongly recommend that you kind of have that rule sheet nearby as much as you can. I think it's not perfect, right? You got to flip all the way back. If you took out the staple and it's in a binder, then it's not bad. You could pop out the rule sheet and put it next to you. I'd recommend that, I think. But let's go through the rules. We are balancing under acidic conditions. You'll notice I have 2 columns on that first page. One was acidic, one was basic. Ignore the basic stuff. Okay, we're not going to do that. It's not too much different. It's just extra steps at the end. So you would start with the acidic rules even if we were going to do it under basic conditions anyway. Rule number 1. Write the oxidation numbers of the elements that are oxidized or reduced. Circle those that change. I don't really care if you circle them, but let's do all the oxidation numbers. That's the first step. What's the oxidation number of an element all by itself with no charge? 0. Any element all by itself with no charge has a 0 oxidation number or a 0 oxidation state. What's the oxidation number of an element with a charge all by itself? Whatever the charge is. Yeah, 1 plus. Same thing over here. Now, this is diatomic, but it's the same concept. It's an element all by itself, no charge. The oxidation state is 0. So what we want to do now is we've got to figure out what was oxidized and what was reduced. I strongly recommend you look for the reduction, because that's the one that makes numerical sense. The reduction is the one that's going down in number or down in value. Okay? So it says for number 2, locate the element oxidized. And then in rule 3, it says locate the element reduced. I kind of recommend the opposite of that, because finding reduction is just easier. If you want to flip rules 2 and 3, you can. Which of those 2 elements did the number decrease? Hydrogen. It went from 1 plus to 0. That is my reduction. How many electrons did it gain to go from 1 to 0? 1. Now, again, gaining electrons, right? Electrons are negatively charged. When you gain electrons, yeah, exactly. It's the opposite of what your brain wants it to be. Okay? If the hydrogen was reduced. If the hydrogen was reduced, the other element, aluminum, must have been oxidized. How many electrons did it lose? Okay. What step are we on now? I think we're on step 4. We did step 2 and 3. We found what was oxidized. We found what was reduced. We bracketed it. We've identified which is what. Now we split this whole nonsense into 2 half reactions. Okay? So we're going to take the oxidation half, put it here. We're going to put the reduction half, put it there. If you remember from last year, leave some space on either side. We need some extra space because we're going to have to add extra things. Okay? So I'm going to write my aluminum, changing into my aluminum 3 plus in the middle to leave some space just in case I need it. And I'm going to write my hydrogen, changing into my hydrogen gas in the middle to leave some space on either side. Rule 5, balance. Okay, let's do that. Balance all other elements other than hydrogen and oxygen. 1 aluminum, 1 aluminum. Golden. All right, that's it. 5.2. Balance oxygen by adding water. I got none. No worry, nothing to do there. Okay, 5.3. Balance hydrogen by adding H1 plus. Okay, we got to do something now. There's H1 plus, there's H2. I have 2 hydrogens there, I have 1 hydrogen here. I need to add more H1 plus.
Why is that not just counting? Balancing. It's not, you're not balancing it, you're adding in.
Well, when you balance, you add coefficients, right? So, I'm sorry, I see what you're saying. You don't always have this as the source of hydrogen. You know what I'm saying? This could be in a compound, and it was circumstantial. It just happened to be H1 plus this time.
Okay.
So it sometimes is not. Step 4, balance the charge by adding negative electrons to the more positive side. I have 0 for a total charge over here. I have 3 plus for a total charge over there. Those 2 need to be equal. The reactant side and the product side of my half reaction must have the exact same charge overall. All I can do now is add electrons. Do I want to add 3 electrons over here or 3 electrons over there? The product side, because electrons are negative, right? So when I add my 3 electrons over here, the total charge on this side is now 0, which matches the total charge on that side. Here's the other thing. This is oxidation, right? And oxidation means what's happening to the electrons. We're losing them. So if we're losing electrons, they better show up on the product side. If you write an oxidation half reaction and you have electrons on the reactant side, that doesn't make any sense. Either you've completely flip-flopped what was oxidation and what was reduction, or something else has gone wrong. They have to be on the product side because we're losing them. Down here, the elements are balanced, the charges are not. How many electrons do I need over here? 2 of them, right? So I have 2 H1 pluses. All right. Step 5 is done. Step 6. The number of electrons used to balance a half reaction should equal the change in oxidation number of the element. Now, this is where last year you might have like looked at that number and you went up here and it's like, ooh, it matches, yay. Or you might have looked at that one and it's like, uh-oh, it doesn't match. I honestly don't even really want you to do this because I trust that you're going to get it right without doing that check. And it makes it a little more confusing because when it doesn't match, then people freak out. Can you see why this doesn't match? Can anyone pick out why down here in my reaction I have 2 electrons, and on our bracket we said it was 1? Yes, that's exactly why. Okay, the oxidation number is changing by a value of 1. The hydrogen is going from 1 plus to 0. But how many hydrogens are doing it? 2 of them. Okay, so the quantity can change that, which doesn't match your bracket, which freaks kids out. Don't check it. Don't even check it. Just trust that you're doing the math right. Because if the charge over here is 0 and the charge over here is 0, you're good. Let me say that a different way. Sorry. If the charge over here and the charge over here match, you're good. Because sometimes it's not 0. Okay? I gotta be careful. All right. Now, step whatever the heck. 7. Let's fix them so that the number of electrons lost equals the number of electrons gained. We got to multiply these half reactions by coefficients so that however many I lose match however many I've gained. Okay? Good old least common factor situation. Okay, did I blow any minds with that? Taken, like, I don't know, 5th grade math maybe? I don't know when you teach that stuff. Probably about right. Okay. Now, when I distribute this, I have 6 electrons, 6 electrons. That's what we want to see. They have to match. Okay, we can't have electrons created or destroyed into nothing. 8. Equivalent items are added if they're on the same side of the arrow or subtracted when on opposite sides. Check to make sure that the elements and charges are balanced. Okay, we're done. We balanced this half, we balanced that half. We fixed the coefficient so that the electrons match. Now we just got to take our values and get the overall balanced reaction. Okay? So, how many aluminums do I have? 2. How many hydrogen ions do I have? How many aluminum ions do I have? How many hydrogen gases do I have? Is there anything else that I need to add? No, right? Because what happens is this is 6 electrons, this is 6 electrons, and then they both just cancel out, right? Because I have them on the product side here, I have them on the reactant side here, and they cancel. So the overall balanced redox reaction for the first one is this: 2, 6, 2, 3. Okay? Try the second one. Use the rules. If you're not feeling confident just winging it, which I wouldn't assume that you are confident just winging it, go through step by step. Step 1, write oxidation numbers. Step 2 and 3, find what's oxidized, find what's reduced. Okay? So on and so forth. Go for it. Try number 2. I guess. It's not as fun as it looks.
Right?
Not possible. So we have to do each of these. And it's not going to find it on that side.
Okay.
So what we could do, we start here.
Oh.
There's nothing.
Oh, I have to do this.
Yeah, you got nothing. We,
Okay. Sounds good.
I wouldn't, always rely on that.
Yeah. That was just harder, so.
And this is the fun stuff. I love balancing. You can be the most complicated redox reaction. It's a good time. That means somebody else. Or somebody just typing in the chat.
Here.
Yeah. That's all.
Really?
Yep.
Just like,
Well, I don't even use it anymore, but anyway, spoiler alert. They actually have a program now on our computers that actually catches all of your attendances. And I get timestamps, so I get to see when you bail on my class. It's kind of cool, I guess. You're there till the bitter end, whatever you want.
If you just join like 4 times on the same thing, then like you keep
What if, like,
coming
yeah,
back.
what's that join that?
I guess then I'd probably assume your internet was giving you troubles that day.
Yeah, but would it say that? Or would it just
Loophole,
say-
there you go. No, yeah, I would say that.
Oh,
Yeah.
you ever seen
Yep.
that? Oh, wow.
It's actually a pretty good program. They actually,
Didn't that happen?
it's way better than it used to be. Yeah, so by the way, your teachers can see when you join and leave classes now. So if you join 5 minutes late and then leave 2 minutes later and just say here, I can see that now.
That's why you go in and out all the time, so I think your internet's bad.
Yeah, I gave you the loophole. You're right.
No, I already knew that.
Oh, okay. Or, you could take your education seriously and stay in class.
I've never done it to your class.
That's good.
So it's later in the day, so. Nice job with that. It was earlier.
Like, they just ramble on, and you're like, okay, I'm not learning.
How is that not my class? That's like the definition of my
No,
class.
but yours is like entertaining. I'm like, actually.
Yours I actually have to pay attention to. Where like if I don't,
I'll take that as a half of
I'm
a
not
compliment.
doing well, so. The other one,
They don't do that for world history. It's not doing that in person.
Dude, world history is the most exciting and engaging topic.
it might be interesting, but it's not taught. in-
Okay, balance your redox. Don't distract me, you children.
I was like, wait, what's the word?
Do your redox. Go. Prepare your answer.
Then I think it's add water on one side and H to the other side.
Follow the rules. They help.
I don't know again the rules. That's probably my fault.
I'll give you a little chunk of more time here, and then I'll jump in.
Can we write like
There we go.
we write it all?
Yes, you do. Write it off.
Yep, so nice.
That's where you add.
Yeah.
So now we're.
Yeah.
So then like after I balance it, then
Add
I add, no wait, yeah,
You add water to fix oxygen.
okay.
You add H1 plus to fix hydrogen. But you got to do it in order. So you fix all the non-hydrogen oxygen first. Fix the oxygen next. Fix the hydrogen last. The order doesn't matter. Really send it. Yeah. Yeah. So if you just run it through steps, there's this first down.
Yeah.
So right now.
Well, if I'm adding H2O to the side that needs more O, so you add it to the reduction that are on the left side, the reaction side. but it's not 7.
Yeah, if you add 9 acres of foliage, but then on the other side, you have to add 14 ions. Yeah, and then I bring the software.
As I've been wandering around, I feel your gears turning, and I feel like you're close, right? Once we knock off the rust, you'll be good to go. It'll come back, I promise. So I'll give you another couple minutes here. At 45 after, maybe I'll do this one and jump in and go through the whole thing, okay? And if you're good, try the next one. Yes. We're gonna get close to finishing. We love that.
For oxidation.
I think she thinks I'm not funny. Isn't that ridiculous? I know. Nice. That's the regular podium. Thanks, Jay. Actually, ooh, who's number one? He's funnier than I am?
Yeah.
Does he just swear more? Or?
Well, he does, but.
What do you do? Britlet with him?
Yeah.
I bet he's got to be more fun in Britlift than he is in Advanced Comp.
I don't have one.
I was looking at it once.
I feel like Advanced Comp is kind of like a serious class, isn't it?
Yeah.
Whereas Britlift, you just read like Shakespeare.
Yep.
Yeah.
The last week.
I know.
Then he'll bring his recorder.
What do you have? What was the first one?
What?
Oh, that one. That's got.
It's like a whole class, like, you ask what monster,
That was so frustrating. You don't even realize how mad we got at him.
Oxidation numbers. I'm going to go through it. 3+, it's just matching the charge. 3+, just matching the charge. Over here, oxidation numbers are by element, right? Not the whole molecule. Okay, we got to do it individually by element. So I have oxygen. Oxygen is always 2-. I've got 7 of them. That's -14 currently. Eventually, I want the total to be -2. So I need to get a +12 for my chromiums. I've got 2 of them, so individually they are 6+. Iron matches the charge. We're good. Step 2 and 3. What's oxidized? What's reduced? Again, the easiest thing to do is look for the number that went down. That's reduction. That's the definition of what reduction is. 3 to 2. Your iron is the reduction, and it's gaining 1 electron. The chromium is the oxidation, and it's losing 3 electrons. Okay. Step 4, I bring this stuff and I split it in half, and I set up my half reactions. Oxidation half reaction. Chromium 3+. The dichromate, Cr2O7, 2-. Reduction, iron 3+, iron 2+. Okay, and now we balance these things. When you get to the balancing, you have to go in order. Okay, if you look at Rule 5, 5.1 says balance every element except for hydrogen and oxygen. I have 1 chromium, I have 2 chromiums. I have to fix that first. Okay, if you skip that step, it's not going to work out. Did you skip it? How'd it go?
Not good.
There you go. See? I speak the truth. Let's fix that first. 2 chromiums, 2 chromiums. The next step, oxygen. How do we fix oxygens? You add water. That sounds weird, but we add water. So I have 7 oxygens. I need 7 oxygens. And I add 7 waters to get that done. And now I've messed up the hydrogens, haven't I? I've just added a whole bunch of hydrogen that wasn't even there before. It's okay. The next step says fix hydrogen by adding H1+. How many H1+s do I need? 14. It's a big number, but we're doing the right thing. Don't let the big numbers scare you. Sometimes when you write big numbers on chem problems, it's like, wait, something's definitely wrong, right? Because normally it's like 1s and 2s and 3s. But in redox, that's not necessarily the case. Make no assumptions. Elements are good. 2 chromiums, 7 oxygens, 14 hydrogens. All the elements are balanced. The charges, not so much. That's the next step. 5.4 says fix the charges by adding electrons. This side currently is 6 positive, right? See that? 2, 3 pluses. Okay, so the total charge on the left is 6 plus. The total charge on the right is 12 plus. Because I have a 2 minus and I have 14 1 plus. So 14 positive minus 2 is 12 plus. 6 plus, 12 plus. How many electrons do I need to add on the product side to make this work out? 6. And you can see why you want to write this in the middle, right? Because if you write it right here, you got nowhere for the water to go. And if you write it too far that way, then you got nowhere for the other stuff to go. Try to center it so you can hopefully add something on either side. The reduction half is way the heck easier. 1 iron, 1 iron. All right. Boom. You say you like this?
Yeah.
I know, right? I know, it's kind of fun. Well, because then my ratio of the irons is off, right? So we have to balance 2 things. We've got to balance like the physical atoms, 1 to 1. We have to balance the charges too. So if I did do 2 of those and 3 of those, the charge would be good. But all of a sudden I've made an iron out of nothing. Yes, man.
Redox only works in water.
It is
Or-
generally in aqueous solutions.
But if you have it somehow not in a good situation, would it still work? And you don't have the H2O.
Correct. There are instances of redox under non-aqueous conditions.
And then
Generally, when we do redox, it's under aqueous. Keep going.
you were kind of working it out with that water, you have to do it.
Yes. Yes. Well, and here's the weird thing with it, right? Combustion is redox. You balance combustion reactions all the time, right? So the aqueous redox ones need to be the whole half method and all the nonsense. But we've done combustion a whole bunch, and that's just a standard balancing situation where we just, do normal coefficients and figure it out. So anyway, electrons are not good, right? 6 up here, 1 down there. Let's multiply the bottom one by 6 to make sure that whatever electrons we lose is the exact same as the electrons that we gain. Got to match, otherwise we're breaking the laws of everything. Okay? Then we transfer all of our numbers up. Iron 3 plus, I have 6 of them. Chromium 3 plus, I have 2 of them. Dichromate, I just have the 1. Iron 2 plus, I have 6. But now, I've got extra stuff.
So that just.
It doesn't matter. We got to add it. The electrons cancel, right? 6, 6, those will cancel. But the waters and the hydrogen ions that we added, they don't cancel. We've got to write those out too. They're important. They're part of the process. So I have to write 7 waters, and I have to write 14 H1 pluses. Okay, obviously my formatting is pretty hideous and ugly. If you have a better way, or if you'd like to rewrite the whole situation, please do so. Okay. Yes.
Do oxidation numbers actually mean anything, or are they just like a number you use to?
They are related. It's it's related to Lewis diagrams, and they can do more than just help us balance redox. But for what we're up to, they're going to help us balance redox, and that's about it. So.
Is it a lot different in bases?
No, actually. So if we were to balance something under basic conditions, we would literally have done absolutely everything the exact same so far. And then we just add a couple steps at the end. What you do is you add hydroxide to both sides to neutralize all the H1 plus and turn it into water. And then you cancel out the waters, and any residual hydroxide just would go on the other side. So it's pretty much, it's almost the exact same thing with like 2 extra steps at the end. I think I have 5 extra steps, but it's really not that complicated. All right, we got 2 minutes. If you're at home, you can run away. We'll pick this up and do the last 3 tomorrow. If you're in front of my face, let's sanitize and call it a day.
Yeah. Oh, I got that.